What we're going to talk about now is something that makes a lot more sense once we've gotten to the point where we're discussing AIDL and binder RPC, because it's something that really figures prominently in that context. So what we're going to talk about here is we're going to start talking about the proxy pattern. And as we'll see, the proxy pattern is a pattern that appeared in a couple of different places. It appeared in the Gang of Four book, where it's focusing primarily on a very simplistic way of doing proxies. And then later, we'll see it appeared in the POSA 1 book, where it was described a bit more generally, focusing on communication that occurs in environments where you're going across address spaces. So we're going to kind of merge these two things together, and we'll talk first about the pattern, and then we'll talk about how the pattern gets applied in the context of Android. So what's the context? Well, the context is, in most environments where you have to cross address spaces, it's not really feasible to access the internal details of an object directly. If it's in a server process, you just can't get to it from the client. You're separated from an abstraction boundary that could be a logical boundary, like you might have with, say, Java, or it might actually be a physical, quote, physical boundary, which is protected by the hardware, where you have things running in separate processes. But whatever the case is, you can't get to something directly. And of course, Android provides this binder RPC mechanism, which we can use to communicate across the backplane of the device to talk between processes that are always on the same device, but in different address spaces. Another part of the context here is that as you start to develop your system over time, it's often the case that you change your mind about where you want your objects to live. Now, this is really easy to motivate when we start talking about a distributed system. In a distributed system where you've got networks involved, you might start out with things perhaps co-located in the same address space or on the same machine for various reasons. Simplicity of programming is the most obvious one. And then as your customers start to scale up or scale out, you want to add more and more and more processing to your solution. So rather than putting everything together in one address space or in one machine, now you've got multiple machines. And so in that case, you may start changing where things reside over time as your system has to grow, or as you do profiling to learn where the hotspots are, where it slows down, and so on and so forth. But the point is that things are going to change over time. So what are the problems? Well, one problem is that manually writing code to marshal and demarshal communication between address spaces is very tedious, error-prone, and just non-portable. It's just a real pain. Nobody wants to write that code. It's hard to maintain. It's hard to optimize. So you'd really like not to have to do that yourself. The second problem is if you were able to rewrite a lot of code every time they read, configure, and redeploy their software to break things up into different partitioning boundaries, that's a lot of work. And if you program with lower-level IPC mechanisms like sockets, for example, the amount of work required to change from communicating between things in the same address space to things on the same machine in different processes to different processes on different machines, it's a lot of work to do that by hand. And so most people just give up very quickly. They say, the heck with it. It's good enough. I'm not going to worry about it. So these are the kinds of impediments that we run into when we start trying to build systems that have to be broken up across different address boundaries. So what's the solution? Well, as you'll see, there's a multi-part solution here. But one piece of the solution is to define something called a proxy. And the proxy essentially acts as a surrogate or an ambassador that gives a particular interface, actually the same interface, to the client, and then allows the implementation of that interface to be someplace else. And that someplace else could be in a different address space on the same machine. It might be in the operating system kernel being accessed by an application running in user level. It might be another process on another machine. We don't really know. We don't really care. All we know is that the proxy is allowing us to abstract and encapsulate the details of where things actually reside. And that'll allow us a lot more flexibility to move things around. So here's how you might do this on Android. You might go ahead and inherit a remote object from a binder, as we've been talking about many times. And this binder then allows you to be able to export that object to the receiver side. Of course, the way in which you get a proxy to this thing is to describe the interface to this via an AIDL file, which says what the methods are and their signatures and so on. And then you run that through the compiler. You get the proxy, which is generated automatically for you. And then when a client invokes a method call on the proxy, it thinks it's accessing something that's local. It says, you know, service.download image or download file or whatever. It looks like it's making a local call when in fact it's actually calling something elsewhere. Now, where that thing resides, you can control in Android by changing various directives in the manifest file. So you can control whether or not the thing is in the same address space or whether it's going to be in a different address space. You get some control over that. But the point is that whether it's in the same or different, the proxy is shielding you from what's actually taking place. Now, as we'll see later, the proxy pattern is going to work together with the Android binder RPC mechanism in order to implement the broker pattern. And we're not going to talk about that quite yet. That's going to come next. But be aware that that's kind of where we're headed on this thing, is to talk about brokers. The proxy is just a piece of that. If we were thinking about this in broader pattern concepts, we would say that the broker was a pattern language and the proxy was a piece of that pattern language. And we'll perhaps talk about that later. OK, so as always, these are not just random assortments of classes thrown together for ad hoc reasons. They fit in some grander scheme. This grander scheme has been around for quite a long time. Some of the early work in this area goes back to the early 1980s. So it's been, what, 30 plus years at this point for a lot of this stuff. It's been around for a while. And the pattern is called the broker pattern. And the pattern is called the proxy pattern. And the intent of this pattern is to be able to provide a surrogate or placeholder for an object to allow another object to access it and control access to it. You can take a look here for more information about the proxy pattern. There's a couple different reasons why you would use this. The typical reason why you would use this pattern is if you need to be able to access an object using something that's more powerful than a simple pointer or a simple reference. Pointers and references that you find in C++ and Java are great when you're talking to objects that are in the same address space. When you start having objects that reside in other address spaces, they don't work so great because they can't reach across those address spaces. So that's when we need to have proxies. Another motivation here is to make it easy to be able to change where the objects reside, local versus remote, or co-located versus remote, without changing the way that you access them. So those are the considerations that might help you. Another thing you might want to do here is if you want to have some kind of strong type checking. Let me add that one just for fun. Let's say if there's, let's see, when there's a benefit from having strong, statically typed method invocations. And what I'm really talking about here, what I'm really comparing and contrasting with, is the approaches that use proxies from other approaches that are based on more message passing. We'll talk about those later. Here's a quick synopsis of the structure and participants in this pattern. It's pretty straightforward. This is the diagram from the Gang of Four book. We have a subject, which is really the thing that's defining an interface. Obviously, in Android, that's the thing that's defined with AIDL. We have the proxy, which is the guy that is shown to the client, which does the magic under the hood we'll talk about in a second to get the method turned into something that can go over to the receiver side, to the real object, the real subject. And in Android, that's, of course, handled by the generated code that's stub.proxy, nested inside the stub class. And then finally, we have the, quote, real subject. And in this case, the real subject would be some combination of stub and the actual implementation in the context of Android. When you start looking at this in a distributed systems lens or through a distributed systems lens, you'll see that the Gang of Four description of this pattern is a little bit meager. And there's other steps going on here to get to the other side and turn it back into a method call. But for the purposes of our discussion right now, just think of proxy being the local surrogate or local placeholder or local ambassador to some object that may reside someplace else. And when you invoke an operation on the proxy, it does stuff, and then it forwards the call onto the real subject to do the work. This set of dynamics diagrams kind of illustrates this point in a little bit more detail. So the client starts out by getting a proxy from someplace, typically from a factory of some kind, a factory method. Once it's got the proxy, it then invokes a method call on it. As you can see here, most of the time, you're using proxies to go across address space boundaries. Not always, but mostly. And so what's happening in this case is that the proxy is turning around and converting the method call that was invoked on it into some kind of message. stripping out or taking the bytes that are coming in as parameters and turning, or the objects that are coming in as parameters, and serializing them into linear byte sequences with a particular encoding format. And then somehow, and this is the part that's not talked about by the proxy pattern, it's getting it over to the real subject to do the work. And when the real subject is done, the call returns, typically synchronously, although you can have variants that do asynchronous interactions. And then it takes the results back, which are in a message format, turns them back into whatever native format is responsible and expected by the caller, and then returns back to the caller. And so either through return value or out parameters or in-out parameters or something, the results are updated and the client gets the results back from the server. So it's basically method to message back to method again. That's kind of the way it works. OK, any questions about the steps, either static or dynamic? So there's a number of interesting consequences of applying this pattern. One of the key ones, and why it gets used so much in distributed systems, is it allows you to, at least in theory, decouple the location of an object from the access to that object. So you can change where the object resides without changing other things. You don't have to change the interface. You don't have a lot of extra work to do on your behalf as a client application developer or as a server application developer. You could also use it to simplify tedious and error-prone details. This is just a little snippet of the code that you would see if you were to peek inside of the download image proxy that's generated for you. And as we've looked at this before, it's kind of messy and ugly, and nobody in their right mind wants to write that code and maintain it by hand. It's just awkward. So we'd much rather have it be done for you by the proxy writer. There are also some potential overheads, however. There's some potential liabilities or downsides with this, one of which is you are at the mercy of the writer of the proxy generator. If the writer of the proxy generator does a good job, then you're in pretty good shape. It's probably equivalent to what you could do by hand. If the writer of the generator of the proxy code does a bad job, you've got lots and lots of overhead, and there's not a whole lot you can do about it unless your middleware gives you the ability to handcraft your own proxies and plug them in place of the ones that are automatically generated. So this is one of those topics that has gone back and forth for decades. There was a time when interface generators were really bad, and so people did a lot of work on optimizing things either by hand or by writing better generators. Just like with everything else, over time people get smarter about this stuff, and so a well-written generator should be competitive to code you would write by hand. In fact, there was some interesting work done maybe, 15 years ago or so by some folks at University of Utah on a technique called Flick, which was an IDL compiler that was heavily optimized to generate code that would be very fast. And it used programming language transformation and optimization techniques to analyze the code that needed to be generated and come up with optimized ways of generating the proxy code. Interesting stuff. Another potential downside, and this really comes back to the issue I added to the slides a second ago, having to do with strong typing. One of the other potential concerns with proxy is it will overly restrict the type system that you have available on the client side. Now this is a sort of a subtle point, and I want to have some discussion about it to see what other people's insights and impressions are about this. So when you start using proxies, you're really saying ahead of time, these are the valid types that can be passed to methods with a particular signature, and here are the results that can come back. You're tightly coupling those things. Now, when you write normal Java code, you write normal C++ code, you do that all the time. So that's not really an unusual thing to do at one level. But when you start moving into a distributed environment, or an environment where you're separating out client and server so that multiple clients are accessing a common shared server, all of a sudden things get more interesting. And there was a fair amount of backlash a number of years ago against strongly and statically typed proxies in middleware for distributed computing systems. And the alternative approach, which you see, by the way, all the time in things like SOAP and other message-based or message-oriented messaging systems, XML-based messaging systems, is stuff where it's more dynamically typed, where you actually create a message, you build up a message piece by piece, usually using some kind of internal coding where you keep track of the type tag, like a tag in XML along with the data. So they're self-describing messages. And you end up, instead of having an interface with lots of different methods with very strongly typed signatures, instead you have one interface called send that takes a message. And the message can be done in some arbitrary self-describing way. So in fact, if you take a look at the messengers in Android, that's kind of the way it is, right? You create a messenger, and it's got a send method. It takes a message, and you put bundles into the message to put anything you want into there. So does anybody want to hazard an opinion about the trade-offs and pros and cons between the proxy-like approach, which is more statically typed, and the message-based approach, which is more dynamically typed? Why would you choose one versus the other? What are the pros and cons?
I like the static typing because you get most of your errors up front from the compiler.
So when you use a statically typed approach, you're letting the compiler and the other tools in the language processing tool chain determine early on when you have inconsistencies between the types that you're creating on the client side and the things that you're passing over to the server side. So strong typing, removing errors. Another thing that comes along with that is often optimization. The more type information is available, usually the more you can optimize things. With strong typing, you often don't have to send over the type information. You can basically have the sender and receiver agree ahead of time. And so the type information isn't sent with a message. Only the data is sent with a message. So the amount of data that's used on the network goes down, and the amount of data to be processed goes down, and so on. So those are arguments in favor of the strongly typed approach. But there's another point of view. I'll never forget when I first started programming back in the mid-'80s, I was reading about Fortran programmers and C programmers who didn't like Pascal. And they would always say, strong typing is for weak minds. So what's the downside with the proxy-based approach, with the stronger typing?
It's less flexible.
Less flexible. And so what that really means in this context is, as your services evolve over time, if you have strong typing, then as your service evolves, all the clients that rely on that service have to also be evolved to take advantage or to utilize the new type information. And so as a result, it becomes, quote, inflexible, because now you've got to go out somehow and change all the clients. And there could be a lot of clients, and a lot of those clients you may not have any control over because they're belonging to some other organization, some other development team, some external group you have no knowledge of whatsoever. So in those environments, especially if you're trying to do things like large-scale enterprise system integration, it's often useful to have a model where you keep the messages dynamically typed. So as you evolve your services, then you can simply have your new clients do new things, add new parts to the message, and when they send it to the service will say, aha, I got a message from a new client, I know how to process that. But the old messages from the old clients will still be handled without requiring changes to the clients. So there's a lot of issues there about trade-offs between forcing changes to the edge of the system, which is what you need to do if you have stronger typing through proxies, versus having the typing decisions done by the service, which gives you more flexibility and dynamism, but is typically slower, has more time and space overhead, and also leads to surprises. As Christoph was just saying, you often don't really realize until the system is running that people are sending you gobbledygook that makes no sense at all. So there's all these interesting trade-offs. So that's a key thing to remember, and probably a good quiz question. What are the trade-offs between the strong typing and dynamic typing in the context of proxy? We'll see. We might or might not see later. There's some use of this in Android, but it's not big enough to maybe warrant it as a full-blown pattern. There's a pattern called extension interface, which is widely used in Microsoft COM and in some parts of enterprise Java Beans, where you basically have these things called components. And a component is basically an object on steroids that exposes multiple interfaces. And each of those interfaces exposed by the component are strongly typed, and they have proxies. And what you do is you have this little kind of 20 questions negotiation take place between the client and the component, where the client goes out and it queries the component and says, do you support this interface? Oh, you don't? OK. Do you support this interface? Ah, you do. OK, thank you. And so it takes what it gets back, and then it makes method calls. So the so-called extension interface is kind of this hybridization between static typing that you get with proxy and more flexibility that you get with messaging. So it kind of gives you the best of both worlds, or the worst of both worlds, depending on how you look at it. Another problem you have with proxy is the fact that it's very difficult to entirely shield the application client from the fact that there's a boundary between sender and receiver. So you might like to pretend as though it's invisible, but invariably it's not. And when things go wrong, there are errors that occur when you start running things in different address spaces that do not occur if things are co-located in the same address space. If you make a method call on an object in the same address space, network unreachable is unlikely to occur, right? Whereas if you're running in something that's going across the internet, then someone might cut the network cable with a backhoe or something like that, or the storm might blow down a wireless tower and you lose connectivity or whatever, right? So these are things that you have to be prepared for when you start programming clients using proxies that you wouldn't have to be prepared for if you were just making normal calls. There's a number of known uses here. Most of these known uses are actually much more interesting in the context of the broker pattern, but they also use proxies, so I'm just mentioning them here. We'll talk about it later. The SUN RPC, or the so-called Open Network Computing RPC, remote procedure call model, which started back in the middle 80s, which was a successor to something that came out of Xerox PARC on remote procedure calls by Andrew Burrell and Bruce Nelson. There's also the distributed computing environment, DCE, which came around the late 80s, which was kind of the end of the line of very convoluted, complicated C-based RPC mechanisms. What came next was the combination of the peanut butter of distribution with the chocolate of objects to form distributed object computing. And you get things like SUN remote method invocation, or Microsoft's DCOM, or the Common Object Request Broker architecture, various kinds of object request brokers in this context, Corba and so on. A lot of stuff done there. They all use proxies very heavily. And then nowadays, now we're 20, 30 years down the road, this stuff resurfaces again, but this time in the context of communication between processes using the binder mechanisms for local interprocess communication on the same device in Android. And it's worth also noticing, if you click on this link here, you'll be taken to a little stub that describes where the Android binder framework came from. It actually came from an earlier work done by BOS, and I think maybe even Palm OS, by a group of people led by Diane Hackborn, who's got the coolest name of programmers in the world. Born to hack, right? We actually have a guy in ISIS called Doug Hackworth, so he's a worthy hacker, I guess. And so they basically wrote this binder, and then they got bought, or they joined the Android development team at some point later, and that's what the Android binder is based on. It's called something called the Open Binder. As I wrap up this section, and then we'll migrate to the next topic, I want to make some interesting observations about proxies. So proxies are a great microcosm of a trend that's been going on in computing for decades, ever since the very beginning of time. And that trend is that useful patterns evolve over time into features provided and supported automatically by various kinds of language processing tools, either programming languages or by tools like AIDL compilers. Here are some examples. If you go back far enough in time, you'll see that the early developers of assembly code were using certain patterns of writing assembly code, and those were things that later found their way into the second generation languages like Fortran and C, where they had things like closed subroutines, or if-else statements, or switch statements, or loops of various kinds of things. Those things all started out by assembly language programmers saying, gosh, if we organize our assembly code in these patterns, it'll be easier for us to maintain. And smart people like John Bacchus, who invented the first Fortran compiler, said, we can actually automate that. We can build a tool that does that for us. It's kind of funny, if you go back in the early days of compilation and second generation languages, there was all kinds of controversy between the super duper assembly language programmers who knew how to write really tight assembly code and do register allocation by hand, and all these newfangled developers who were trying to write compilers to automate that stuff. And there was a lot of controversy. People said, you'll never be able to write a compiler that can generate code better than I can write an assembly, and so on and so forth. which always amazes me and amuses me to no end. Whenever new technology comes along that's threatening to the status quo, people always start out by downplaying its relevance, and then later on they go, oh, well, you know, maybe it solves a few problems, but it doesn't solve all the problems. And then at some point they've been completely overwhelmed and overtaken, and you don't even think twice. You just do it without even stop to think about it. By the way, that meta pattern or mega pattern is described very nicely in a series of books by Clayton Christensen, who writes about the innovator's dilemma and the so-called disruptive technologies that come along. I won't go into it in detail right now, but it's worth looking into because it's great stuff. So the point there is that, you know, what was once patterns then find their way into language features. Another set of examples, if you go back to so what I just described was from like the early 60s. You go into the early 70s, there were still a lot of people writing code in assembly language, a lot of people writing code in C at that time, and they were beginning to write bigger systems. And they had to figure out some way of hiding information so that their application developers, which were usually themselves, because the programs weren't all that big, they wouldn't end up making tight coupling on implementation details that were likely to change over time. So if you recall, when we do 251, we talk about stacks. And we talk about different ways of hiding the representation of the stack to avoid writing code that relies on a particular implementation. So what happened there is people began to come up with patterns for hiding information. So like in C, you make stuff static, or you define a header file with a bunch of functions and so on. And what grew out of that information hiding approach, the patterns of information hiding, really turned into the language features for things like classes, packages, and other ways of being able to automatically and through automation and through automatic checking and language tools, be able to make sure that things really do stay private. You can't access stuff. You can make access control checks to keep things from happening. When C++ first started out, and for actually at least a decade or so after it started out, it didn't have any support for parameterized types, which was uncomfortable and inconvenient. Java was the same way for a long time, by the way. So back in those days, people would follow patterns of preprocessor directives or writing little tools with sed and awk and so on in order to annotate their code with template-like syntax that would then be preprocessed and turned into actual code. That experience with macros and these other tools led to people writing templates and adding them to C++ as a template feature. There's lots and lots and lots more examples. So people doing things like the iterator pattern that we learn in 251, and we've talked about here a little bit. The iterator pattern is something that used to be done by convention. Nowadays, you take a look at Java, you take a look at C++11, they've baked the iterator pattern into the language with things like range-based for loops or the for each loop in Java and so on. So once again, you see this never-ending trend towards moving stuff from convention into automation. And there's pros and cons with that, of course.